get true numbers by having a good precision and a good accuracy. Precision is how closely individual measurements agree with one another, and accuracy is how closely individual measurements agree with the accepted value. Let's say there are three targets here, and the accepted value are these dots in the middle. And if I am in a range and I'm shooting, and let's say I shoot all my shots right here, I'm nowhere near the target. We call this a this is precise, but it's not accurate. Let me just write that again. Precise. It's precise, but not accurate. Let's say I shoot this target and I shoot all over the place. In this case, you can see my shots are all over this target. In this case, this is not precise and it's not accurate. But let me show you another example. Let's say if I have all my shots right in the target, we call this precise and accurate. All right. Also, in chemistry, we deal with significant figures. So all digits of a measured quantity, including the uncertain ones. So the more significant figures you have, the greater the precision for that measurement. Um, when you're adding and subtracting numbers, remember that the results has the same number of decimal places as the measured with the fewest decimal places. What do I mean by that? Let's say I collected these two numbers through a measurement, and this is an addition. The addition rule says that the number, the value that I show has to be coming from the measurement with the fewest decimal places. So the fewest decimal places in this example is 0.01 and not this number, because you can see 1, 2 from the decimal. This is 2 decimal places, and this has 1, 2, 3 decimal places. So the fewest one is this number. So my answer would be 2 decimal places. So if I add those two numbers, what do I get? So 0.9 plus 0.01, I get 0.91, and my answer would be 0.91. I do not have a zero after that because that would make it 3 decimal places, but I need to be in 2 decimal places. Same thing with this, with the answer here. We need to go with the measured with the fewest decimal places. So if we collect these two numbers in the experiment, this one has how many decimal places? 1, 2, and this one 1, 2, 3. So 2 is lower than 3. Our answer would be 2 decimal places. So when we're dealing with multiplication and division, the result containing the same number of significant figures as the measured with the fewest significant figures. So if we're multiplying these two numbers, our answer would have significant figures with the measurement that has the lowest sig figs. So in this case, we have 1, 2 sig figs, but here we have 1, 2, 3, 4 sig figs. So for, I'm gonna just show abbreviate like this, sig figs. But here we have two sig figs. Whoops. Sig figs. So our answer will have two sig figs. So if we multiply this number, what do we get? Um, 6.221 times 5.2. We get 0.91, and the answer is in two sig figs already, so 0.91. All right, when we're dealing with multiplication and division, there's a zero rule. So zeros between numbers are always sig figs. So for example, there's a zero in between here. We count this as a sig fig. So one significant figure, two, three. So here we have three sig figs. How many sig figs do we have here? The next rule says that zeros at the beginning of the number is never sig fig. So we don't count these two. We only count this one, and this one. So three, right? Here, the next rule says that zero at the end of the number is sig fig if the number contains decimal. Here we have 1, 2, 3. We don't count these two. Here we have 3. Here we have 1, 2, 3. But we have a decimal, so we count these 4, 5. 5 here. Let's move on to dimensional analysis. So problem solving method that uses the fact that any number or expression can be multiplied or divided by 1 without changing its value. What do I mean by that? So in chemistry, we do a lot of dimensional analysis. In other words, conversions. So I have this example. I have 10 milliliter and I want to convert it to a liter. How do I do that? So usually you want to start with the number that are given. So this is given. So 10 milliliter. And you set your multiplication as a ratio. Here you want to have ml, and here you want to have L. The reason you want to have ml in the denominator, because on numerator here, to make it easier, just put a 1 here so you can see your numbers in the numerator. So in the numerator you have ml. To cancel these two out and have an answer as in liter, you need to cancel these two. So this cancels out, this cancels out, this unit cancels out, and leaves us with L, which is liter. So how many milliliters in liters? So we know that 1000 milliliter equals to 1 liter. So then we do a calculation. 10 divided by 1 times 1 divided by 1000. Let's do that here. 10 divided by 1 and 1 divided by 2. So division, dividing by 1 does nothing for us. And here we're just going to divide 10 divided by 1000. Our answer is 0.01. 0.01, and that's in L liters. This is a 1 conversion and usually takes, we call it the 1 step. Sometimes there's many steps to convert something. For example, I have here 2 or more conversion factors. Here I have 10 meters per second, and I want to convert it by doing dimensional analysis into miles per hour. Um, let's see how we're going to do this problem. So let's say we have 10 meters per second. Like I said, you can make this look like a ratio if you just put a 1 here and multiply, do dimensional analysis. Uh, you can start by canceling out any of these. Doesn't matter which one you want to start with. I like to start with seconds, and I want to convert it to hours. So for time, we need hours. So what I do is, I know they're in 1 minute, 60 seconds. So you can see here that my seconds cancels out and it leaves me with minutes. But I don't want it in minutes, I want it in hours. So I keep going. Times. I know that in 1 hour, there's 60 minutes. And right away you can see that my minutes cancels out and leaves me with the answer in hours. Good, so we're done with time conversion. All we need to convert now is meters into miles. So I know that in 1,000 meters, there's 1 kilometer. And you can see that my meters cancels out here. And this number usually will be given to you, maybe an exam, or you can look this up. And we know that in 1.609 kilometers, there's 1 mile. And here we canceled out kilometers and we're left with miles. So our answer will have miles per hour. And if we do our calculation, let's do that quickly. So how I usually do this is 10 divided by 1. I negate the 1. I just move on to the next step, times 60. So 10 times 60. I get 600, and then times that again by 60 because we can negate 1 here, times 60. I go ahead, divide that by 1,000. And then divide that number by 1.609. 0.609. And we get 22 point dot dot dot. So here we want to keep it in two significant figures, two sig figs. So 222 is a good answer, miles per hour.